Hi everybody, happy Friday the 13th. Bad day for a quiz. Tomorrow's Valentine's Day, call your mom. This is lecture 12. We're going to be discussing section 7.2, not 7.2, 7.6. Section 7.6 is applications of integration. All right, first part of the lecture, I want to talk about just basic introduction to work done by a force acting through a distance. So the simplest case, so if we have a force F acting through a distance D, then work equals force times distance. So for example, force of 7 newtons acting on an object that moves from position 3 to position 11. So a picture of this would be something like this. So we could have an object, have a force acting on it, and the object moves from there to there. So the force would be, the work would be the force times the distance, which would be the force times change in x, so would be 7 newtons times x equals, this should say meters. So 7 newtons times 8 meters. So that would be 56 Newton meters. That unit is a unit of work called a joule, Joule. Now if I make a picture of this, I could graph the force as a function of x. Well, the force is constant, so the force is just the number 7. And we move the object from 3 to 11, so there's our distance of 8. And so that number 56 is this area. Okay, so that seems simple enough. But mathematicians love to gripe about how physicists and engineers are sloppy with math. But the thing is, if you read these math books, the mathematicians are sloppy with their physics. This object is moving from here to here, and there's the force, so the work is 56 joules, right? Well, what if it's, what if Jace is actually pushing that cart this way, and I'm trying to push back at it, and I'm exerting this force of 7 newtons while the cart is going this way? Well, then actually, I have not done any work. Actually, the cart has done work on me, because the direction of motion is the negative of the direction of the force. So there's an accounting you have to do these work problems correctly and safely. You have to have your axes set up so you have an idea of a positive x direction for the the motion being in a positive x direction, and then the force needs to be described as having a direction. So the force of 7 newtons in the positive x direction acting on an object that moves in that positive x direction does this amount of work. If if Jace is pushing this cart, and I'm actually sitting on top of the cart with all of my, I weigh 100 pounds, so, and the cart moves across this floor, I haven't done any work because my force is down, but the cart is moving perpendicular to the direction of my force. So there's an accounting you have to do that our book just doesn't do. So you can get negative signs, incorrect signs if you do the accounting wrong, and the book won't really. You might be confused as to why it seems so hard, and the book makes it seem so easy. It's because they miraculously just show you the. They sweep all the orientation stuff, the positive and negative directions, positive and negative forces. They sweep all that under the rug. Okay, so this is the case with a variable force. I'm sorry, constant force. So a variable force variable in the sense that it depends on where you are. So maybe your force looks like this. Well, the work to move the object from A to B is still this area. So the work done to move the object from x equals A to x equals B is, still called capital W, but instead of just being force times distance, it's the area under this curve, so the integral as x goes from A to B of f of x dx, or integral of f of x. Okay, so let's do an example. Force acting on object is capital F of x equals cosine of pi x over 3 newtons, and it's in the positive x direction, whatever that is. How much work is done on the object? To move it, question A, from x equals 1 meter to x equals 1.5 meter. Question B, from x equals 1.5 meter to x equals 2 meters. And finally, question C, from x equals 1 meter to x equals 2 meter. Well, for A, we're going to have the work being the integral from x equals 1 meter to 1.5 meter of the force, which is cos pi x over 3. Okay, well that's going to be the integral of cos is sine, but we have to do a substitution because the constant's inside. So this ends up being the antiderivative of sine is a sine pi x over 3. And then you divide by pi over 3, in other words, or you multiply by 3 over pi. So there's my antiderivative, and I have to evaluate that. And this should be newtons. Newtons. So it's another thing about the book is they don't do a careful accounting of the units. Physics courses, they would do a better job of this. So when I integrate this, I get sine pi x over 3 newtons. Yeah, I'm not going to do this because it's a can of worms. So I'm just going to stick to the book's style of things. So this is the number of newtons, and x is the number of meters. Okay, so we have to evaluate from x equals 1 to x equals 1.5. So this is 3 over pi times sine of 1.5 pi over 3 minus sine of 1 pi over 3. Oh, but 1.5 pi over 3 is just 0.5 pi. In other words, sine of pi over 2. And this is minus sine of pi over 3. So I get 3 over pi is my thing, my constant in front. And then I have the number 1 minus the number square root of 3 over 2. And I'm just going to leave it like that. And we have a force of newtons acting through distances of meters. So this is going to be joules. Okay, for question B, it's going to be similar, but we're going to be integrating from 1.5 to 2 of cos pi x over 3. So we'll get all the way down to here, and I'm going to get to 3 over pi times sine of 2 pi over 3 minus sine of 1.5 pi over 3. So that's 3 over pi times sine of 2 pi over 3 minus sine of pi over 2. Now remember, the sine of 2 pi over 3 is square root of 3 over 2. If you do a unit circle, here's pi over 3. The ray created by that angle crosses the unit circle at 1/2 comma square root of 3 over 2. Here's 2 pi over 3, and the ray created by that angle crosses the unit circle at minus 1/2 square root of 3 over 2. The y-coordinates of those points are the same, and those are the values of sine. So this is 3 over pi times square root of 3 over 2 minus 1. Now, how big of numbers are these? How big is square root of 3? Say again?
Like 1.7 or something?
Yeah, 1.732 roughly. So square root of 3 over 2 is about 0.85 or so, 0.86. So that's about 0.86. So that minus 1 is actually a negative quantity. Over here, 1 minus 0.86, that's a positive quantity. Okay, so question C, the work in going from 1 to 2, well, I can break that up into two integrals. I don't have to go through all this again. The integral from 1 to 1.5 plus the integral from 1.5 to 2. So I end up with 3 over pi times the quantity 1 minus square root of 3 over 2 plus, again, 3 over pi times the quantity square root of 3 over 2 minus 1. So it ends up being 0. How do you do 0 work? Well, you know, for the first part of the motion, the force is going the same direction as the movement. So the force is doing work on the object. But in the second part of the motion, the force is going in the opposite direction of the motion. So the force is actually doing a negative work on the object. The object's doing work on the force, you could say. So anyway, those add up to 0. So that's part 1, just the introduction to the idea of a force that depends on position. Part 2 is springs, ideal springs. So for an ideal spring, force equals Kx, the spring constant. And x is the displacement from equilibrium. Position, or from the natural position. So what does this mean? Well, you can picture something like a, don't worry about gravity. Let's have a frictionless surface. Let's have a wall that's not going to move. And let's have a spring attached to this wall. And then let's have a handle on that spring. So this has spring constant K. Spring constant is K. So this is x equals 0. That's a natural position. So suppose I want to stretch that spring out to here. Well, I'm going to have to grab that handle and I'm going to have to pull. So this is the x direction, and the force that I'm exerting on that spring is in that direction. I mean, I'm pulling, but that's the same as you know, pushing on the handle in that direction. So if I wanted to move it, say, you know, 5 meters, then so if I've stretched it to here, x equals 5, then the force that I would be exerting on that handle would be 5k, whatever k is. If I want to stretch the spring out to x equals 13, so then I want to have the handle sitting here, which is at x equals 13, well, the force I would have to be exerting on it would be 13k, whatever k is. And that force would be in this direction. Now, what if I want to compress that spring so that the spring, instead of being at x equals 0, is maybe at x equals minus 3. So I've moved the handle from here to here. Well, when the handle is here, that spring is being compressed. I'm going to have to be pushing that direction. And that makes sense. F equals kx. If the position is x equals minus 3, F would be minus 3k, whatever k is. So you get that the force, so again, if I'm sitting out here at position X, the force on the spring would be K, whatever K is, times that value of X. Force in the positive X direction. If X turns out to be a negative number, then force is going to turn out to be a force that's pointing that way. All right. So here's an example. A spring has natural position or natural length 20 centimeters. And it's known that if you exert a 25 Newton force on the spring, it will stretch the spring to 30 centimeters. So the question is this: how much work is done to stretch the spring from 20 to 25 centimeters? So that's the question. Well, when we stretch the spring from 20 to 25 centimeters, what we care about is the displacement from the natural position. The natural length of 20 centimeters, which is 0.2 meters. So when x equals, when the position is 20 centimeters, then x would be 0, because the spring is at its natural position. When position is 25 centimeters, then at that point x equals 5 centimeters, which is 0.05 meters. And when x equals 30, when position, or I should say when the length, so when the length of the spring is 30 centimeters, then x would be 10 centimeters, which is 0.1 meters. So just to get our variables established. Okay, so for the question, work is going to be the integral from, well, when the spring is 20 centimeters long to 25 centimeters long, that's going to be an integral from x equals 0 to x equals 0.05. It's these two positions that we're talking, these two x's that we're talking about. And we're going to be integrating kx. So that's going to be, the integral is going to be k times x squared over 2, and I've got to evaluate from x equals 0 to x equals 0.05. So I'm going to have k times 0.05 squared over 2. Well, shoot, what's k? Well, let's use the given information. We have that the force equals kx. The given information says when the force is 25 newtons, the spring will be stretched to a length of 30. In other words, x equals 10 centimeters. So 25 equals k times 30. So k equals, k times 10. And that 25 newtons, and that should be not 10, it should be 0.1, 0.1 meters. So k is going to be 25 over 0.1. In other words, k is 250. So let's go back and be careful about the units here. So in this equation, force equals kx. So let's put units in here. 25 newtons equals k times 0.1 meters. So when I divide, I get 250 newtons per meter. And in this equation, 0.05, that's the number of meters. That's 0.05 meters being squared. And so if I take this k and I put it into that formula for W, I get W equals that k, so 250 newtons per meter times 0.05 meters squared over 2. So look, so I end up with 250. So we have two kinds of arithmetic going on here. We have, or two kinds of algebra. We have the algebra of the numbers, and we have the algebra of the units. So we have 250, that number, times 0.05 squared. Now, 5 squared would be 25, but 0.05 moves the decimal over 4 units when I square it. So 0.0025, that's 0.05 squared. And then I've got to divide by 2. And what is my algebra of my units? I have newtons, meters squared divided by meters. So in other words, I have Newton meters surviving. Okay, 25 times 25 is 625. But I have to move the decimal place, let's see, 1 to the right, but then 4 to the left. So in other words, 0.625 over 2. So 0.3125, and this is joules. I think that's right. Now, notice if I have a spring attached to that wall and its equilibrium, its natural position is like right here, and I want to stretch it to here, then I've got to pull with some force. I've got to be pushing that handle in this direction. If I want to stretch it farther, that spring is going to be pulling back with more force against me. So I'm going to have more force to get it farther out. So So as you stretch the spring out, the force you're exerting on it has to increase. So here's a really cool problem. It's known that six joules of work is required to stretch a spring from 10 centimeters long to 12 centimeters long. So that's 0.1 meter to length 12 centimeters, which is 0.12 meters. So that's known. I don't know what the natural length is. It's also known, but that 10 joules of work is required to stretch the spring from length 12 centimeters, so that's 0.12 meters, to 14 centimeters. So that makes sense. You know, I do some work. I don't know where what the natural position of the spring is, but I stretch it from 10 to 12, and it took some work. But I'm stretching the spring, so it's going to be it's going to take more and more force to keep this string stretched. So to stretch it another 2 centimeters is going to require more work. So it makes sense that it took more work to stretch it from 12 centimeters to 14 centimeters than it took to stretch it from 10 to 12. So this is a really cool problem. The question is, what's the natural length of the spring? Question is, what is the natural length of the spring? So this is a really hard problem because I don't know what my natural position is. So I know what my length is, but I don't know what the natural length is. Well, we know that 6 joules is the integral of kx from some a to some b. Well, now what is my a and what's my b? Well, I don't know. I mean, I know that the initial length was 10, but that's not my x. My x is 10 or 0.1 minus the natural length. So let's call this length L. And my ending length is 12 centimeters, but my x is going to be, so in other words, 0.12 meters minus L. So remember, when we integrate this, we get kx squared over 2, and we have to integrate from x, we have to evaluate from x equals, well, that first one, 0.1 minus L, to the second one, 0.12 minus L. So this is a terrible looking calculation. So k times 0.12 minus L squared minus 0.1 minus L squared all over 2. And so notice this is an equation involving K and L. We get another equation involving K and L this way. We know that 10 joules is how much work it takes to go from 0.12 minus L to 0.14 minus L of Kx. So when I go through all those, when I do this, I get K times 0.14 minus L squared minus the quantity 0.12 minus L squared, all over 2. So notice, this is another equation involving the same two unknowns, K and L. I don't know what K is. I don't know what the natural length is. We don't care what K is. So I can solve these equations and get values for both of these things. I could figure out a value for K, I could figure out a value for L, but I'm only being asked for L. So notice if I take the first equation, 6 equals that stuff, and I take the second equation, which says 10 equals that stuff, if I divide this equation by that equation, I get, so we're going to solve for L. If I divide the second equation by the first, I get 10 divided by 6 equals K times 0.14 minus L squared minus the quantity 0.12 minus L squared over 2, but divided by, again, K over 2, 0.12 minus L squared minus 0.1 minus L squared. It looks terrible, but if you actually do the arithmetic, it's not so bad. You end up getting a value for L. The natural length of the spring is, drum roll, 8 centimeters. So 0.8 meters, 0.08 meters. So it's a very cool problem. It's one that it's not assigned, but I just think it's really beautiful. All right, let's do our quiz. So put phones away. Maybe could you all move to the right, and Jason, Sam, could you move to the